Welcome to lesson 5.2, titled The First Derivative Test, and this is a follow-up to 5.1 where we talked about extreme values, absolute maxima and minima, and in this section we're going to take a more in-depth look at those concepts from 5.1. And where we'll start is a review of a key term from 5.1, critical points. And if you recall, these are points where a function can have an extreme, a max or a min. And where we said these critical points can occur are endpoints on a closed interval, and for those, that's only absolute extrema. The two other spots for critical points, which we're going to talk about a lot more in this lesson, are where the first derivative is equal to 0, so a slope of 0, and where the first derivative does not exist, but the original function does. So our sharp corners, our cusps, places where we have a point but we don't have a defined slope. And so if you look to the function on the left, we have at x equals 3 a spot where our slope is 0. So thinking about breaking down our critical points, we're not going to worry about ends. This is an open interval, but we do have a spot where f prime equals 0 at x equals 3. We have another one here at x equals 5. And those appear to be the only points where the derivative equals 0. Moving on to where the derivative does not exist, we have a nice sharp point right here at x equals 6. And so those are the only critical values for this function. And visually, you can already spot where the relative extrema are in this problem. But what we're going to delve farther into in this lesson is how we can talk about behavior and key points on a function using just information we get from its first derivative, and creating what's known as a sign chart for our first derivative. So what we're going to do with this sign chart idea is we're going to create a number line using the critical points or the critical values for f of x. So I'm going to create a number line. On the end, I'm going to label it f prime to show that we're talking about the first derivative. And I'm going to put those three values we have for our critical points, 3, 5, and 6. And what we're going to do after that is determine the sign for our derivative for all intervals on this sign chart. And how we're going to do that, we can determine the sign of our derivative by testing out values in between. So maybe something like, we can test out what's going on at x equals 2, 4, and so on down the line. Visually, it's going to be a lot easier. Like if I look at x equals 2, right around here, I would notice my function is increasing at that point, which means my first derivative is positive. F prime is greater than 0 right there. If I were to look at a spot like x equals 4, I would notice my function's decreasing. My slopes are negative. Looking at 5.5, again, I'm back to increasing. So I get another positive. And at 7, I've got a decreasing function. So f prime is negative. And notice how over all these intervals we created, these 4 intervals, f prime keeps that same sign. F prime can only change signs at a critical value. And so the idea of this first derivative sign chart, which we've just created, is that it leads directly into the title of this section, the first derivative test. So really treat this as kind of being step 3 to the process. 1, we've created our number line. 2, we've determined signs for the derivative in between each of our critical points. And what our first derivative test says, if f of x has a critical point at x equals c, and f of c is defined, then we have 2 things that could be happening. 1, this c f of c is a relative maximum if f prime changes from positive increasing to negative decreasing, or cf of c is a relative minimum if f prime changes from negative, so our function is decreasing, to positive, increasing. And put a little star over here for yourself to tell you if there's no sign change, you have neither. So using this information, if we go back and look at our original graph and compare it to our sign chart from the first derivative, notice how at 3, we have a switch from a positive derivative to a negative derivative, a switch from increase to decrease, and at x equals 3, we have a relative max, which lines up with part A of what we've said from our first derivative test. This negative to positive switch coincides with a relative minimum. And even at this spot where the derivative did not exist, at x equals 6, we have a change from positive to negative on the first derivative. And notice, since our function was still defined at x equals 6, this still shows up as a relative maximum. And so the rest of this lesson takes a look at what this first derivative test can help us do and the types of situations we can apply it to. The first being curve sketching. We can draw a pretty accurate approximation of a function just based on the information we get off its first derivative. So sketching something like f of x equals x cubed minus 3 halves x squared plus 2, without having a calculator, the best we could do would be to set up a table of values, pick out random x and y values, and hope that we can get a good idea of what this looks like. Or we can take a look at its derivative. And the derivative in this case would be 3x squared minus 3x. And going one step further, let's go ahead and I see an opportunity for factoring, so we're going to take it. Because what I would like to do in this problem is set up that first derivative sign chart. So let's find spots where that first derivative is equal to 0. So we're going to set 3x times x minus 1 equal to 0, and realize that we have zeros for our derivative at 0 and 1. Spots where it does not exist, well, the original function was a polynomial, its derivative is a polynomial, so that will be none. And so what we'll do off to the side, let's set up our sign chart with these values. Open interval, so I'll leave both ends of the sign chart open, and place my values 0 and 1 right here. And so this is going to be a little bit different than what we started with at the beginning of the notes because we don't have a graph already set up. So what we're going to have to do is we're going to have to think, well, I know from negative infinity to 0, f prime keeps the same sign. It can only change signs at a critical point. So I'm going to use a test value to help me figure out what sign the derivative takes from negative infinity up to 0, and I'll use a test value of negative 1. In between 0 and 1, let's use something like 0.5, and from 1 to infinity, we'll use 2. What we're going to do is test those out in the first derivative, and marking this at the end will help to remind you what function you should plug your test values into. So we'll start with f prime of negative 1, and I'm going to plug it into the factored form. And if you choose to, go ahead and get the values. The big thing is you just need to be confident in what the overall sign is. Because in this case, I have a positive 3 times a negative 1. And I know negative 1 minus 1 is also going to be negative. Positive times a negative is just going to be a positive value. I don't really care what that value is. F prime of 0.5. And again, don't care about the value, because I know this is positive 3 times a positive 0.5, and 0.5 minus 1 will be negative. Overall, that will be a negative number. So using shortcuts like this just helps us be a little bit more efficient in our work. Focus on what the key information is, which is just the overall sign, not the numerical value. In this case, I'll have a positive 3 times a positive 2. 2 minus 1 will also be positive. We'll get positives here. And just notice the amount of information this gives us. We have a positive to negative switch at x equals 0, which means this has to be a relative max on f of x. We have a negative to positive at x equals 1, so this has to be a spot for a relative minimum on f of x. Now I'm still going to go back, and I am going to go ahead and set up a t-chart, but I'm only going to do that with the two values that I care about, where the relative max and min are located. I'm going to go back and plug this into the original. That's because I am going to approximate this curve, but these are two spots I know I can get graphed accurately. So I know I can graph the point 0, 2 for my relative max, and plugging in 1 will give me positive 3 halves. So 1, 3 halves would be my relative min. And the best part of this first derivative test is I also know that my function is increasing when f prime is positive, which is from negative infinity to 0, along with 1 to infinity. That's when f of x is increasing. I also know f of x will be decreasing when we have negative slopes, when f prime is negative, which is going to be from 0 to 1. And putting that all together, a function that increases from negative infinity to 0, decreases from 0 to 1, increases from 1 to infinity, with these relative maximum input in place, I'm going to get a function that looks like this. Now, using this information to actually sketch a graph of a function, not necessarily something we care about doing, not something we'll be tested on, but all the principles that are there, identifying where a function's increasing or decreasing based on its derivative, identifying the location of maxima and minima based on its first derivative, those are all things that we should be able to break down. So make sure that you feel comfortable with all the individual parts of this problem, but realize putting them together in this fashion, probably not something we're concerned with. So what I'd like you to go ahead and do is try what we just saw on this function located below, f of x equals 1/2 x minus sine of x, trying to get a sketch of that graph on the interval 0 to 2 pi. XY coordinate plane over here, going from 0 up to 2 pi, and see if you can put all the principles in place that we just looked at to get a relatively accurate sketch of what this function might look like. Please pause the video, and when you're ready to check your results, go ahead and restart. Okay, so hopefully, big first step was that you had the derivative correct. Setting that equal to 0, that involves some knowledge of the unit circle. No spots where cosine is going to not exist, so no spots where f prime doesn't exist. And the big thing is your sign chart. Notice how I closed this one off because I only wanted to go from 0 to 2 pi, not wide open, included my critical values. And the big thing is your test values. Especially when dealing with trig, make sure you're good at locating test values on certain intervals. I picked pi over 6, pi, and 11 pi over 6. And again, not worried about final values, just worried about the final sign of my answer. And we go negative to positive to negative. So I know I have something that's decreasing, increasing, then decreasing. And I've also figured out that I'm going to have a relative min at x equals pi over 3 because of that negative to positive change, and a relative max at 5 pi over 3 due to the positive to negative change. So the last thing I'm going to do is go back and evaluate my original function at these key values. And also thinking back to 5.1, I'm going to include 0 and 2 pi, always wanting to look at endpoints. There's spots where we could have absolute extrema, but also they're going to be easy spots for us to graph this function. And starting on those, f of 0 would be 0, f of 2 pi would be pi. Notice how these are going to be a little bit trickier. We want to be able to graph accurately, and the exact values we get out of this are not going to look very nice. Negative 0.342 and 3.484. So I'm going to go ahead and mark this off by pi over 3's. There's pi over 3. Count by 1's on the y-axis, negative 1 and positive 1, and graph our points. We had 0, 0. We had pi over 3 and negative 0.342, so maybe about there. At 5 pi over 3, back over here, we were at 3.484, so just about 3.5. And at 2 pi, we were at pi, so about 3.14, right around there. And we get a decent idea of what this graph would look like on this interval. But now we move on to the big problems that we should be able to answer for any function. Finding intervals of increase, decrease given a function, and relative extrema, because all this information comes from the first derivative. So starting with f of x equals x squared minus 4 quantity raised to the 2/3 power, f prime of x would be 2/3 x squared minus 4 to the negative 1/3 times 2x. And getting that a little bit simpler, we'll get 4x over 3 times the cube root of x squared minus 4. So find our spots where this is equal to 0. Well, this is a fraction, so that would be where the numerator equals 0, which happens at 0. And the does not exist is anything that makes that denominator equal to 0, which will be when x squared minus 4 equals 0. And you can factor it, solve for x either way. We will get that this derivative does not exist at negative 2 and positive 2. But notice how the domain for the original function is all real numbers, so we can still have extrema at negative 2 and positive 2. And setting up our sign chart, negative 2, 0, and 2. We'll work with test values like negative 3, negative 1, 1, and 3. And when dealing with these, again, trust that you can just get the overall sign. Please do not try to spend all of your valuable time getting the exact answers. Because for this, I know the numerator is going to be negative. You're going to be doing the cube root of 9 minus 4. That's a positive value. 3 times that will make it positive. Overall, this will be a negative. Working with negative 1. Again, you put in as much writing, as much work as you need to get your final result. But I know we're going to have a negative number up top. This negative 1 squared minus 4 is going to be a negative. Cube root of a negative stays negative. Overall, negative divided by a negative is a positive. And it sounds quick, but those are the types of quick decisions we need to be able to make. Dealing with 1, well, the nice part is you're squaring the values in that cube root. So the result for 1 is going to be the exact same as the result for negative 1 down there. The only difference is up top, this will be a positive value from 4 times 1 over a negative. Same thing, you've already worked with negative 3. 4 times 3 is going to be a positive, but notice how working with a positive 3 gets you the exact same result as working with a negative 3 down in the denominator. So it will also be positive. And we can fill in our signs on our sign chart. And that will allow us to answer all of our questions. F of x is increasing on the intervals where f prime is positive. So from negative 2 to 0, and from 2 to infinity. F of x is decreasing on the interval negative infinity to negative 2, and from 0 to 2. And we'll have a relative max where I have that positive to negative switch at x equals 0. I don't see any other positive to negative switch. And there's also a relative min at x equals negative 2, where our derivative switches from negative to positive. There's also another one at x equals positive 2. And moving to our second of these type of problems, we have y equals 8x over x squared plus 1. Notice again on this one, our domain is all real numbers. This denominator can never equal 0, so we don't have to worry about any asymptotes or discontinuities. And getting our derivative, which you can go with y prime dy dx, whichever notation you choose. Notice this one will have to go with quotient rule. So low d high minus high d low all over our bottom function squared. I'm going to go ahead and expand this out so that we can hopefully get something a little bit easier to work with. I'm going to go one more step and factor that numerator. Because again, we kind of have to anticipate what's coming up, and we want to get this into the form that's going to be easiest to work with. So let's start with our derivative being equal to 0. And that's going to happen when that numerator, this negative 8 times x squared minus 1 equals 0, which will happen at x equals 1 and x equals negative 1. Going to our does not exist case for the derivative, notice that would be when x squared plus 1 equals 0, which can't happen. That would be only for imaginary solutions, so we're going to say none. And here's where the repetition takes over. We're going to go ahead and set up our number line for y prime with our two critical values. -1 and +1, and set up some test values with -2 here, 0 in the middle, +2 out on the end, and plug those into our y prime. And as I've been doing, I'm going to go with the simplest form to work with. I'm going to go with that factored form. But the one nice part about this is notice your denominator is always going to be positive. You're taking x squared, which is going to make it positive, adding 1, squaring that result. I don't even need to worry about plugging anything in down there. I know it's always going to be positive. It's the numerator I'm worried about. And this will be a -8 times a 4 minus 1. That 4 minus 1 is going to be a positive number, +3. Overall, that numerator is going to be negative. Negative divided by positive gives me a negative value. And again, if I already know the denominator is always going to be positive, I can completely ignore that and focus just on what's going on up top. And in this case, if I put a 0 in, that's going to make this -8 times what would end up being a negative number. It's going to make that numerator positive, and we'll get an overall positive result. And again, just to remind you, you do however much work you need to do. If you feel more comfortable getting the values, get them. But like I said, I'm always looking for the more efficient route. And this one, -8 times what would be a positive number, will give us a negative in the numerator. Negative divided by a positive is a negative result. And let's once again break down all of our key information. This y function is increasing when its derivative is positive, so from -1 to 1. Y is decreasing when our y prime is negative, so from -infinity to -1, and from 1 to +infinity, which will give us a relative max happening at x equals 1, and a relative min occurring when x equals -1. Again, just make notes to yourself. This is a positive to negative switch. This one is a negative to positive switch on our y prime. And so what we're going to end on is these two problems where we're given a graph of f prime. Notice that it says f prime. We want to find all critical points and all relative extrema. And one thing I guess I should add is for f of x, for its original function, the function that this represents the derivative for. And we can do that by remembering our critical points are any endpoints, which I don't have on this first one. So we're going to go ahead, we're going to note the endpoints here just to say none. Spots where our derivative equals 0, which occurs at -3, 1, and 3. And spots where the derivative does not exist, we have none of those. So we have all of our critical points. And if I want to think about relative extrema on f, I'm going to use this to set up a sign chart. So with -3, 1, and 3 there. And we're going to think about test values just like we did when we had a function. You can use the values I've given. You can use any values you want to. Because the key thing is when I think of what's happening at, say, -4, notice how at -4, your derivative is going to be positive. It's going to be way positive. I can't even find a point there. When we look at 0, notice at 0, your derivative is down here, which means it's negative over this whole span, and you can visually see that. At 2, and actually everywhere between 1 and 3, the derivative is positive, and after 3, we switch back to negative, which will give us relative max at, so we have our first one at -3 on this positive to negative switch. We also have one at +3. And for relative min, we only have one of those. That's happening at x equals 1, where I have my negative to positive switch. So what I'd like you to do is look at the second graph, the one on the right, and try this analysis for yourself and set up your sign chart directly from a graph of the derivative. So go ahead and pause the video and try this last one for yourself. Restart the video when you are ready to look at the results. Okay, so go ahead and compare your results with mine. Notice a couple things. This time I cut out endpoints as even being a consideration. Relative extrema can't occur there anyway, only absolute can. So I made my focus f prime equal to 0 and f prime does not exist. Found 3 critical points that way. The f prime does not exist. You could include x equals -4 if you want, but again, endpoint, not too important. The sign chart, notice I didn't put arrows at the end, not unbounded. I am locked between -4 and 3. And we had one relative max at x equals -2, one at x equals 0 for our relative min, and notice we can confirm nothing about x equals +2 because we had a positive to positive. We didn't actually switch signs, so it's not a relative extrema on the original function. And so that ends lesson 5.2, a slightly bigger lesson, one that has a lot of vital information in it, a lot of direct connections you can take from 5.1. Like I said, just going a little bit more in depth on those principles about extrema, specifically about how we can locate relative extrema by using our first derivative, and also how we can break down intervals of increase and decrease. So a lot of key stuff, and it would be very important for you to make sure you get that summarized. Make sure we review these notes before going into the practice, and when you're ready, go ahead and see if we can put this information to good use. Thank you for watching.